Alright, so now we're going to take a look at the polar form of a complex number, which is really just a way that we can express a complex number instead of just giving its real and imaginary parts, express it like it's a vector that we know that it is. So here's an arbitrary complex number. I put it in the first quadrant, but everything we're going to do is going to be valid regardless of the quadrant that we're in. So we want to express this as a vector. So I'm just going to draw the vector first. This has a magnitude, which I'm going to call r, that's the length of the vector, and a direction, which I'll call theta, which is that standard position angle. Now, just like we've always done, we're going to drop down a perpendicular. So now we have this right triangle. This side along the bottom of the right triangle, this has to be the same as the real part, so that's x. The vertical side length has to be equal to the imaginary part, that's y. And now we're going to find r and theta if we know x and y. So let's say I want to get an equation that uses r, theta, and x, right? So I'm isolating using the real part this time. And if I use the cosine function, thinking SOHCAHTOA, that tells me that cosine theta is equal to x over r, which means that x is equal to r times cosine theta. Hopefully this is a little bit familiar. This is just like the work we did when we were working with vectors. If I want to, instead of getting an equation for x, I want to focus on y here, then I'm going to switch to use the sine function. So SOHCAHTOA tells us that sine theta is y over r, which means that y is equal to r sine theta. So now let's take what we know here, and we're going to start by taking the complex number we were given, x plus yj, and I'm just going to replace x and y with the expressions that we found. So we have r cosine theta plus r sine theta times j. I'm going to factor out the common factor of r. So we have r times, parentheses, cosine theta plus, I'm going to write the j in front, j times sine theta. This is a polar form. Now, just like when we are expressing or writing out what a vector is, it's not uncommon to abbreviate this as r with an angle theta. When we know we're talking about complex numbers, it's understood that these are equivalent expressions. Little bit of vocabulary. R, the magnitude of the number, is also called the modulus. It is also equal to the absolute value. So, we're used to, when we're working with just real numbers, think of absolute value as, whatever that number is, just make sure it's positive. But absolute value always means its distance from zero, or its distance from the origin in the case of a two-dimensional system. So when we find that distance, that is equal to the absolute value. And theta, that direction, is often called the argument of the number. So when we write it this way using the cosine and the sine, we call this a trigonometric form, is one variation of polar form. We can also write it as in an exponential form, which we're going to do later in the section, but they're both considered polar form. And just a word of caution, when we are finding magnitude and direction, or actually in particular, when we're finding the direction of a complex number, we have to be a little bit careful. If we're finding the direction, we use the arctan function, and we just have to make sure that we're finding the that we find the reference angle and make an adjustment for what quadrant that it's in, just like we did when we were working with vectors. Okay, so let's write this complex number in trigonometric form. So we're going to find r and theta. The first thing I like to do here is just plot it, and I don't have to be accurate. Like, it doesn't have to be super accurate. Like, I'm really just trying to make sure I keep in mind what quadrant we're in. And so this is 3 plus 4j. It's in the first quadrant. So something like that. There's theta, there's r. So I'm going to find the magnitude. Let's see, if I know the real and imaginary parts, we can find magnitude just like we did when we were working with vectors. I'm going to scroll up real quick, and we can just kind of develop some of this right here, just in general. But if the relationship between r and x and y is that r squared is equal to x squared plus y squared, so we get that magnitude using Pythagoras like we always did. And then when we find theta, we know that theta is tan of y over x, so the theta reference is arctan, absolute y over absolute x, just like we did when we were working with vectors. So let's find r. R is going to be the absolute value, 3 squared plus 4 squared. So, sorry, not absolute value, square root of 3 squared plus 4 squared. That's 9 plus 16, which is 25, so we get r is equal to 5. This is in the first quadrant, so when I find the angle, I don't have to make any adjustments. Theta is just arctan of 4 over 3. And arctan 4 over 3 is 53.1 degrees. So 3 plus 4j is 5 times cosine 53.1 degrees plus j sine of 53.1 degrees. You could also say it's 5 at an angle of 53.1 degrees. And then there's also one other kind of abbreviated notation. In most math books, instead of using j, they use I. And so you might see the notation, instead of this, you might see r cis theta, where this part here stands for cosine I sine. And those just mean the same thing. All right, let's try another one. Again, I'm going to start just by plotting it so I keep in mind what quadrant we're in. Negative real, negative imaginary, that means we're over here. So when I find theta, I'm going to find the reference angle, and then I'm going to add it to 180 to get the angle. I'll start first with r. We're going to use Pythagoras. We get 3.75. And for theta, I know I'm going to take the reference angle and add it to 180. So I'm just going to do that in one go here. So 180 plus arctan of 3.12 over 2.08. To 36.3 degrees. So this is 3.75 cosine 236.3 degrees plus j sine 236.3 degrees. Okay, let's do another one. Here, they're giving us a polar form, and they want us to find rectangular form. This is really actually almost simple in that the execution, there's not a lot to do. Well, all we're going to do is just distribute that 2.5 and then put the stuff in our calculator. So I know this is 2.5 times cosine 315 degrees plus 2.5 times sine of 315 degrees times j. I'm just going to use my calculator to find the real part and then the imaginary part. So you have 1.77 negative 1.77. So we have 1.77 minus 1.77j. There's the rectangular form. A couple of observations we can make right off, and this becomes obvious when we keep in mind the graphical representation, sort of what these complex numbers look like in the plane. So here's the complex plane, right, with our real axis here and our imaginary axis there. If a number is real, pure real, no imaginary part, it's on the real line, that means that the angle has to be 0 degrees if it's positive real, or 180 degrees if it's negative real. If a number is purely imaginary, then, and there's no real part, that means that the angle has to be either 90 degrees if it's a positive pure imaginary, like positive 2j, that's a 90 degree, or 270 degrees if it's a negative imaginary, so like negative 2j or negative 5j. Those would be down here, right on the imaginary axis. And keeping that in mind, there's sometimes it'll take almost no work at all to find polar form. So if I want the polar form of the complex number 5, right? So this is right here. I know that r is 5, right? That's its distance from the origin. And it's a positive real, so that angle is 0 degrees. So this is 5 at an angle of 0 degrees. Negative 3j, that's just straight down here. So its magnitude is 3, and the angle is 270. Okay, so I alluded to earlier that there's another way to express these in polar form, and that's the exponential form. We have to begin with this really remarkable fact, which is a little bit beyond the scope of this course, but for folks who might end up taking, calculus and up through Calc 2, then you kind of get to a point where you see why this is true. For now, I mean, I'm still amazed when I think about the fact that this equation is true, that r times e to the j times theta. Right, so we're raising the j times theta is in the exponent on e there. That's equal to r cosine theta plus j sine theta. Now, one quick difference here is that theta has to be in radians when we're using exponential form. But it's still just defining a number, it's still a polar form because we're defining a number by its modulus and argument, right, by r and theta. That's what makes it polar. So let's say we want to find the complex number in exponential form. So 3 plus 4j. Now we already knew, right, that this was, we already did the example. Let's go back and find it. Here it is. We found that it was 5 at an angle of 53.1 degrees. So we don't necessarily have to recreate that work. Oops, here we go. What we need to do, though, is take this 53.1 degrees and convert it to radians. I get 0.9268. And so that means this is 5 times e to the 0.9268j. And there's the exponential form. If we want to take this polar form, this trigonometric form, or I guess it's sort of a polar shorthand form, and put it in the specifically exponential form, then we're going to do the same thing we did in just this last one. I got to convert that angle to radians. So 136.3 degrees. 180 in the bottom, pi rads up top, gives us, oops, 2.379 radians. And so this is 8.5 times e to the 2.379j. Let's do another one. So here they gave it to us in rectangular form. I don't think it's one we worked out earlier. So we got to find both r and theta. We're going to use Pythagoras to find r as usual. I get 8.04. Now let's plot this, right? 3.07 minus 7.43j. That's got to be a fourth quadrant number. So I'm going to find the reference angle and subtract it from not 360 this time, but 2 pi. I'm going to have my calculator in radian mode, subtract it from 2 pi. So 2 pi minus arctan of 7.43 divided by 3.07. I get 5.104. So this is 8.04 times e to the 5.104j. Going the other way around, we got 2 times e to the 4.8j. They want us to put it in trigonometric form. Now, look, you can, if you like degrees, you could use degrees when you put it in trig form, but there's nothing wrong with using radians. So you might decide to just write this as 2 times cosine 4.8 plus j sine 4.8, and that's fine. You can convert to degrees if you want, but you don't have to. To put it in rectangular form, just going to proceed as we did in that previous example, where I'm just going to take this modulus here, the 2, and distribute it throughout to get the real and imaginary parts. So 2 cosine 4.8 plus 2 sine 4.8 times j. I'm in radian mode, so just going to put in 4.8 for my angle. We get 0.175 for the real part. And sine 4.8, oh, times 2. Oops. Negative 1.99, so minus 1.99j. All right, let's try another one. Here they've started out, we have this number, they gave us an exponential form, and then they're cubing it. So the cube of that number we want to write in trigonometric form. So we just want to find r and theta for what we get when we cube this out. And this example is a great illustration of why we love this exponential form. It's going to make some things easier, and we're going to explore that a lot more in the next section, but we're going to get a sneak peek right here. If I am taking 1.846 times e to this stuff, and we're cubing it. Look, we have a product that we're cubing. We already know our rules of exponents, right? We've been working on those for a long time. We know that we can distribute an exponent over multiplication. I'm going to do that here. So I got 1.846 cubed times e to the 0.87j cubed. Now let's focus on that second factor there. I've got stuff I'm raising to a power, right? E to the stuff, and then I'm cubing it. We know that when we're raising a power to a power, we can multiply the exponents. And now I'm going to use the calculator to finish this out. So 1.846 cubed is 6.291. And now I'm just going to multiply, 0.87 times 3. 2.61. So this is e to the 2.61j. And there it is. Having this exponential form made raising this number to a power really simple for us. We were able to take advantage of our rules of exponents, and that's going to be a major theme in the next section. All right, we're going to close out with just a summary of how we can express a complex number. We started out, this is our first introduction, with rectangular form, right? That's what we did first, x plus yj. When we visualize it, the x and the y, they're like the coordinates, right? The real and imaginary coordinates when we put it in the plane. And then we could also, when we see it in the plane, define it by its distance from the origin, that's r, and the angle, right? Its direction. And so we call that polar form. These are all called polar form. If you are asked to do a problem and express the answer in polar form, you can take your pick. It doesn't matter. The only time it matters is if you are specifically asked for trigonometric form or exponential form, and then you just have to make sure that you're using that correct form. I'm going to end with an interesting fact. We're going to find the rectangular form of the number e to the j pi. Now, we can do this by finding the trigonometric form and doing some distributing, but we can also do this really simply by visualizing it. So, here's the complex plane. Right, there's our real axis. There's our imaginary axis, e to the j pi. So theta is pi radians. That means we are all the way over on the negative real axis. And so that's theta. And r is in fact equal to 1. Right? So, because e to the j times pi, that's 1 times e to the j times pi. So r is equal to 1. So that means that we are over here at a distance of 1 away. The angle is pi. That means we have to be at the real number, -1. That means that e to the j pi is equal to -1, or in other words, e to the j pi plus 1 equals 0. I want to talk about both of these equations, right? They're equivalent equations, just different ways to write the same fact. I'll start out with the bottom one. This is a really in all of mathematics, in all the history of mathematics, there are 5 uber fundamental numbers. They are 0 and 1, e, j, and pi. And as it turns out, there's a really simple looking equation that relates all of them together. And then moving up here, right, to this top equation, we'll just note that, like, you know, pi and e are both what we call transcendental numbers. They're not just irrational, they're transcendental. They are way far out, okay? So we're taking this transcendental number, e, we're raising it to this imaginary transcendental number up there, j times pi. And when we do that, we get a completely normal number, -1, right? It's an integer. And that just sort of blows me away every time I think about it. So there's a fun fact to close out this section. In the next section, we'll see why we love polar form so much and how it makes our lives a lot easier.